Good morning and welcome to this talk on simple test equipment. Later on Sunday, Alan W2AEW is presenting another test equipment video, and he will be diving deeper into using the more complicated stuff. I will be trying to keep it a little bit more basic and feature test equipment that you can build. Rather than plaster the slides with links and making you rush to note them down, I will upload some slide notes to the convention page of the G4WIF website. After my wife found blobs of solder welded to the new carpet, it was strongly suggested that I take further radio work out into the garden. Hence the shed, and that was 30 years ago. It's proven a good investment. At the beginning, projects wouldn't always work. I learnt to build test equipment that would show me where I had gone wrong, and eventually it provided a better way to understanding. In the early days there wasn't much choice. Commercial test gear was outside my budget. A returning theme in this talk will take us to Pete's article on direct conversion receivers, which turned out to be a very popular inclusion in SPRAT. By the time this presentation airs, Pete will probably be heading towards 100 requests for his Arduino code. I do recognise that using Arduino in projects is yet another hurdle to climb, and although I'll mention it where I've employed them, I will suggest alternatives. If some of the content is beyond where your skills have developed so far, then please don't be discouraged. We probably wouldn't want a hobby that we mastered quickly. It probably wouldn't sustain our interest. Ham radio has kept me fascinated for over 45 years, and I don't imagine it will stop anytime soon. So some of the testing methods I'll show today will employ various methods and tools to characterize the bandpass filter in Pete's article. Filters often involve winding coils, and that incurs stripping of enamel from wire, which has been known to not always work. So visually you can't tell that the filter is working. You have to test it. Of course, many of these homemade testers can be used for other purposes. George often used to quote William of Ockham, who said, "It is vain to do with more what you could do with less." Well, this is the less part. It's very simple to build, and it does work very well indeed. And when I need to test an audio amplifier, I reach for this. When this tone generator is applied to an audio amplifier input, you could distinctly hear it at the output and stages between. You can see that I put the schematic on the case, but if I didn't do that, it's usually printed and folded up inside for later reference. That way years later I stand a chance of fixing it. If it's an Arduino project, then I save all the details and code and I write it to a thumb drive and tuck that inside. In recent years I've started to get to grips with simulation software. One of the reasons that I like Microcap is that the schematics look so much better than some other simulation software. The results are more presentable for articles, where in my view the LT Spice schematic tool is not as attractive, but you shouldn't dismiss LT Spice. It's very powerful and very popular. More on that later. Here you can see a comparison between the real-world tests on the right and the simulation on the left. What I would probably have missed on the oscilloscope was that initial pulse that occurred when power was applied. The simulation software will catch it though. Hopefully you can see the shape of the real output signal is pretty much identical to the simulation. The positive going half cycles look like a nice sine wave, and the lower negative going half cycles have the same slightly distorted shape. For use as a signal injector it is fine, and you could even just stick your finger on the input of an amplifier instead and listen to the amplified hum. Of course, your simulation is only as good as the circuit you have drawn and the tests that you run on it. I regularly collaborate with Nick, G8INE, and we've co-authored quite a few documents together. Nick uses LT Spice, and I use Microcap. If we get the same simulated results, then we know we're on the right track. Pete Giuliano N6QW uses LT Spice, as does his solder smoke partner Bill Mirror N2CQR. Probably your best bet if you have to pick one as a beginner, is to go with LT Spice. First, because of the terrific support in place, and secondly, because it's being continually developed. The oscilloscope is a device that displays voltage against time, and is therefore said to display signals in the time domain. Aside from things like multimeters, when you can afford it, an oscilloscope is so very useful. Being able to apply the test leads to a circuit and see a visual representation of what is happening is very revealing. It's best to avoid the gimmick 15 quid oscilloscope kits from China. They won't show you much of what's happening at radio frequencies. Analog oscilloscopes are available second-hand, and probably even digital oscilloscopes too. The only new oscilloscopes you will get now are digital. If you'd like a deeper understanding of the difference, Alan, W2AEW, gave a talk on each type in the Ham Radio Workbench podcast in August and September 2016. What you can see on the oscilloscope now is wideband noise. Which brings me to this device. Every workbench will at some time benefit from a wideband noise generator. These work due to what happens when you reverse bias a Zener diode by just the right amount. They create a lot of noise. Then you amplify it a bit using whatever suitable transistors you have in your junk box. There's really a need to stick to the transistor specified. It was probably chosen because of what the author had in his junk box at the time. On the Spectrum Analyser you will see signals in the frequency domain. That's low frequency to the left and high to the right. The amplitude of the signal is the vertical scale. As you can see, that noise is right across the spectrum. If you were to zoom in, there would still be continuous signals, and that's why it is so useful. The fact that the output slopes is unimportant when testing filters, as within the filter's narrow area of interest there is no real difference in amplitude. There is an article in SPRAT 187 that shows even simple homemade test gear can show you what is happening in the frequency domain. There was a time when many hams verified the absence of harmonics on a transmission with a simple absorption wave meter. None of my spectrum analyzers have what's called a tracking generator. This is a built-in oscillator that you can set to scan across chosen frequencies, and then it's used as an input to the device under test. I've never really been troubled by not having a tracking generator, as the wideband noise source works pretty well, and although the signal appears a little fuzzy to start with on the Spectrum Analyser, most analyzers have an averaging function, and you can see that working in this slide. There is no end of great websites where you can design a filter, whether it's a bandpass filter like this, or a low-pass filter, or a high-pass filter. You just enter the numbers for the frequencies that you want to affect, and then you can often compare the different topologies of filter that there are. You can choose filters with lots of stages or just a few. In his articles, George G3RJV used harmonic filters for QRP transmitter output designed by Ed Weatherhold, W3NQN. These are documented on the G-QRP website, and there are also files for Quicksmith modelling software for each filter, so that you can examine how well they work and you can tinker with the component values to see what happens. You can see in this slide that I modelled the bandpass filter in Pete's SPRAT article, and then after I built it, I tested it with a nano VNA. Clearly they're pretty much identical, and Pete would have done the simulation work first too. Many articles that include filters will not include this level of detail, so you can see that simulating them yourself is a good way to verify your finished filter is working as it should. The noise generator shown here came from eBay. If you Google nose source BG7TBL, you'll find a lot of information. Yes, it really is spelt nose source. When you wind toroids with enamel copper wire, it's easy not to clean enough of it off and you get a dry joint. Then the filter doesn't work and you won't know if you can't test it. Before I got my first Spectrum Analyser, The photo shows my ICOM 725 and the S-meter displayed the frequency responses very well. I simply tuned the receiver across just under 7 MHz and up to around 8, and you could see where the filter's attenuation was low. This was my first foray into network analyzers, and really my first awareness of the work done by Farhan VU2 ESE. He called this the Sweeperino. It was also the first time that I collaborated with Nick G8INE, and through our own inexperience it's fair to say that the build didn't go well to start with. Having someone to bounce ideas off and to compare tests was invaluable. We both ended up with the most useful of tools. Farhan used an SI570 chip as the oscillator, and it operated up to VHF frequencies. It doesn't work below about 5 MHz, so 80 meter and top band couldn't be covered. The instant reading on the LCD was useful, as was Farhan's BC software, which you can see on the next slide. Nick and I both like to keep notes to help us keep track and to remind us in later years how the equipment worked. So you will find a lot of Sweeperino information from the both of us on my blog. The following year we built the S&A Junior, designed by Dwayne Schmidtkoffer, KV4QB. This was based on a DDS chip that covered all of the HS bands up to 30 MHz, and it had a nice TFT screen where scan results were displayed. The input measuring side was classic W7ZOI. More on that later. Dwayne has a very good blog at the address given in my slide notes. This screen grab shown is from the SPRAT software that Farhan wrote to interface with the Sweeperino. Here I've tested a 20 meter bandpass filter. 14 MHz is in the middle. When you set up the Sweeperino, you connect the input to the output with a good cable and adjust for 0 dB attenuation. Then when you test the filter, you can see that in the passband that you have around 5 dB insertion loss. This is not an unusual figure. From the drawing you can see that the Sweeperino is two separate items. The oscillator that is sweeping across the chosen frequencies, it's like a tracking generator on the Spectrum Analyser. On the right hand side is doing the level measuring of the response through the device under test. Here you can see the Sweeperino LCD showing the signal at 6 MHz and the level of the signal received through the filter. As I advance the frequency, the response changes. The Sweeperino and the S&A Junior both contain the same measuring circuit, and that's from this QST article shown on this slide. It has been much copied and tweaked over the years. Wes and Bob described a very simple two-chip design that measures accurately over a wide frequency range, and the output is displayed on a simple moving coil meter. Both the Sweeperino and the S&A Junior have additional Arduino circuitry which measures the output from chip U3A shown in this slide, and then it displays the results on an LCD or a TFT screen. So without that, the construction gets very much easier. If there's a downside to this classic design, it is that the AD8307 is mostly only available now in surface mount form. And at first that can seem daunting, but with adapter boards like the one shown here, it's really not hard. These boards are available from G-QRP sales. Here you can see the measured frequency response of Wes and Bob's design. It's pretty flat up to 600 MHz and beyond. My radio interest barely reached beyond 30 MHz, but even the UHF enthusiasts would be pleased with this kind of frequency response. This is how you might use a signal generator and Wes and Bob's meter. I've only ever owned 3 proper signal generators, and this Altai shown here was number 2. The previous one, made by Advance, was a valve-based device, and it took up a lot of room in a 5x7 shed. I found a review of the Altair in a 1994 Practical Wireless, so obviously it's quite old, but being solid state it takes up so much less room. And it was an excellent rally find about 15 years ago. I only paid about 20 quid for it, so don't write off the old stuff. Using the signal generator, I can sweep through the filter passband, looking at the RF power meter for where the signal is greater. If you're building Pete's DC receiver, then you may have first built the VFO, so you could use that instead of a signal generator. However, the SI5351 is known to die suddenly if the output is shorted, so it may be best to attach an attenuator. A 50 ohm 20 dB pi attenuator would, if the output was shorted, present around 50 ohms across the SI5351, and that shouldn't upset it too much. If your signal generator presents a 50 ohm output, that's fine. Otherwise, to ensure that the filter sees 50 ohm termination, you can attach, say, a 3 dB attenuator to both sides. More on attenuators later. But here's another way you can check that filter's working with simpler equipment. Watch the meter and the tuning dial. As you can see, this setup works much as the previous slide, but with simpler test gear. I should have used a bigger meter when creating this slide, but by then most of my treasures were packed ready for the house move. My thanks to Bob, G4WIF, for his article on diode probes. I started my working life at KW Electronics, and they were not noted for their transistorized ham equipment. It was all valves, and all had mains power supplies. But I was around people that understood the dangers of high voltage electricity. Grabbing the wrong wire can really spoil your day. But you can't avoid mains electricity completely if you build your own power supplies. So if you're a beginner, please get help and advice, or splurge on, and this goes against the grain, a commercial variable unit for home brewing. Otherwise, at the low voltages we normally play with, you're not likely to come to much harm. I found this case at a rally, and it even came with a meter. I think it started life as an old valve voltmeter. Some of the insides got thrown away, and I installed the circuit on the next slide. I must have made this sometime in the 90s. At the heart of this power supply is the L200 chip. That appeared in the Mappling catalogue one year, and the data included made me want to buy one to experiment. You can still actually buy that chip today. The data sheet says delivering 2 amps at a voltage variable from 2.8 volts to 36 volts. The L200 voltage regulator is a versatile device that simplifies the design of linear supplies. At the top of the circuit diagram you can see 3 resistors selected by a switch. Those 3 resistors allow you to select a point which current limiting takes place. Mine was selected to set to 10 milliamps, 100 milliamp and 1 amp. More recently I rather fancied a power supply that allowed a quite granular control, and the modules shown above on the right became available and started to get good reviews. Even Dave Jones on EEV blog seemed to be impressed. It's a complete unit, and all you have to do is add a voltage source higher than the one you want to output. Something like the same basic linear power supply as shown in the shaded section of the old power supply would work. There are also complete switch mode power supply modules that you can buy to go with the control module, which does of course have switch mode circuitry too. Where it says in minus and in plus is where the input supply goes, and the out connections go to the terminals at the front of the supply. Mine are marked 20 volt variable. Because I had the room, I provided a fixed 12 volt output too, which comes from an additional buck converter. Here you can see the inside view. The case was a repurposed item of lab equipment that went into the recycling skip at my school. Switch mode power supplies have a bit of a reputation for being noisy, but that hasn't been my experience most of the time. Base stations nowadays are powered by 40 amp or more switches, and they apparently work okay, and I found them to be pretty quiet. The really tiny buck converters that are thumb size work well instead of the usual three-legged linear regulators. They don't get hot, and they're usually adjustable. And now a little break from using test gear and some advice on how you can construct them. In the days of valves, components used to be mounted on tag strips. Later we had variabled, which I never got on with. I watched some videos made by Chuck Adams, K5FO, where he showed layouts printed from a laser printer onto paper and then transferred to the copper board for etching with some kind of acid. I fancied trying that, and the G3RJV oscillator, shown here, is one example. I could have been more traditional and mounted the components on the reverse side and drilled holes for the leads. But I have an aversion to all that drilling lots of holes, and there's no reason they shouldn't be mounted on the top. Chuck Adams called this Muppet style for some reason, not connected I suppose with Kermit and his friends. Bill cuts his pads to the required size with a pair of hand shears. Like many constructors, he makes things in a modular way, and you can see he's even marked his board that you can see the separate sections. There's also another reason in this case, because it's a transmitter output stage, and they can often become oscillators. He left room to add screening if needed. Nick the Vic has made some very impressive transceivers, and if you've seen them, you'll recall that he builds them into bread bins. His YouTube channel is excellent, and his teaching style is very approachable for people starting out. Nick uses a Dremel tool with an engraver bit that removes copper to make pads. And if the pads don't end up being perfectly square, does that really matter when it works as efficiently as it does for Nick? With all the examples in these next slides, I know that the constructor has planned the layout first. Some make nice drawings like Nick does and is shown here. I can't draw for toffee, so I'll cover my method in the next slide. Just lately I've rather taken to using perf board, but I've found if you just go by the schematic and start mounting components, it's easy to get into trouble. Planning the layout first is required, and so I use PCB layout software, and I can move components around and then print out the layout double size and then poke components into the perf board. The PCB layout also shows me where I have to connect wires underneath. As a visual clue, I mark the ground points with a red dot so that I know that they all need to be connected together. One bonus is that with the press of a button my PCB software does a copper fill, and then I can etch a PCB if I want and only etch a minimum of copper. The common language of PCB software is called Gerber, and Nick's PCB design software can export to this format to eventually become G-code, and this is what drives his CNC machine. But even though I might use perf board and Nick creates boards as shown here, we can exchange designs by sharing the Gerber files. Pete N6QW is currently noodling on an article that describes his method of creating PCBs using a CNC, and he often uses what I think of as a chessboard pattern, which looks quite neat and it's easy to work on. Note the lack of drilling required. He must hate drilling too. This is the RF amplifier from the N6QW direct conversion receiver. On the next slide you'll see how I can test the plug-in bandpass filter that I also show here. Consider the flexibility that this gives me. Right now this is a single band receiver, but if I unplugged the filter and replaced it with a different board that had band switching, that could also take a number of filters. It could easily expand into a multi-band radio. Using plug-and sockets in your projects means that these homemade adapters would allow you to take a disconnected module and attach any test device, such as a network analyzer. On the left hand side of the RF amplifier you can see some connectors that are at 90 degrees. A lot of my module interconnects use these. So back to test equipment and a circuit that I spotted in the QRP Quarterly magazine. The article was written by Gary Breed, K9AY. One IC divides the crystal frequency by 16. The other IC takes the square wave and converts it to very narrow pulses with sharp rise times. But the comb generator is also great for producing harmonics that reach really high frequencies. And the comb generator can also be treated like a wideband noise generator. I've used it for testing low pass or band pass filters, but even with it switched to 25 kHz markers, they may be too far apart to test some narrow crystal filters. So a comb generator can provide accurate calibration points. This is the mighty midget receiver made by Bill N2CQR. With accurate markers you'd know where to put the dymo tape. As you can see, I added some signal level control as well as the frequency selection. The inside view shows the comb generator etched on a printed circuit board, and to the left is a very small buck converter that I used instead of a 5V linear voltage regulator. Return loss bridges are very simple to build. The enclosure that I used was just over an inch wide and tall, so the cave inside was quite tiny. The PCB is simply a piece of copper where I used a craft knife to create a few islands where some surface mount resistors are mounted. There's no end of instruction material for using return loss bridges on the internet. This was the article, but there are many similar designs. It is R3 that determines the impedance that you're testing for. If you made it a 75 ohm resistor, then you'd be able to test TV systems, for instance. In the slide notes there's a link to a very useful return loss bridge article. Here you can see how it is all connected. The noise source is the generator, and the detector in this case is a TV dongle. It could be an oscilloscope or a spectrum analyzer. These cheap TV dongles can be adapted for use to being an SDR receiver. Even the standard waterfall display, such as you get with SDR Sharp or similar, will show an antenna is heading towards resonance when used in this setup. But there are simple Spectrum Analyser applications that do a better job. This software was from a company called Ear to Oak. Sadly, that company seems to have disappeared from the internet, but the author does have a GitHub site, and I'll link to that in my slide notes. There's also a very informative website called rtl-sdr.com. I'll link to that too. But why is the display sloping like that towards 30 megahertz? To explain, I'll show you another trace, and this was a screen grab when I was testing another filter. In this case it was a low pass filter intended to attenuate harmonics from a top band transmission. I've shown that a simple Zener diode noise generator tends to fall off in output as the frequency rises. But if we look at the output from a comb generator on a Spectrum Analyser, we can see how flat the amplitude is. And if instead we use the comb generator or a noise generator with a more flatter output to test this aerial with the return loss bridge, we would get constant amplitude. And as you can see, this is much more useful. We can actually see how well the antenna is matched on all three bands. But you can also see that the antenna resonance for the 10 meter band is more like 27 megahertz. which is not good. This obviously needs a little bit of attention. The two ways of measuring are related, and you can easily find conversion charts. A terrible match might be, say, a 1 dB return loss. One that was 14 dB would be an SWR of 1.5 to 1. So you can use SDR radios as test equipment. TV dongles can cost as little as £10. They work as SDR receivers with the right software to way above 1 GHz. I've used one to track aircraft. They don't work at all well down in the HF bands, and in that case you can build or buy a converter that precedes the dongle. These devices cost very little and are fun to play with. In recent years, some very good wide-band coverage SDR receivers have become available. The excellent RSP1A from SDR Play currently sells for £99, but it can be more than just a radio. You can download free Spectrum Analyser software from SDR Play, and here you can see that I was able to test a homemade mixer. The Analyzer software allows me to look at the mixer output and see the very low level of the two input frequencies that have crept through. I can also see the sum and difference products, which are far higher in amplitude. So a note about digital signal generators. It was something that a few years ago a good friend had recently bought for himself, and as he's done before, he put temptation my way by letting me play with it. The user interface was a bit odd. They've got a lot better recently, but it produces two unique outputs at any frequency up to 25 MHz, and sine and square and triangular waves, and at any phase difference from each other. It's rock steady, and I've also used it as a temporary VFO. So I bought one, and now I have two signal generators. Oh, and it's also a frequency counter. Also in the slide I show some 10 dB-ish attenuators. They are homemade and not quite as perfect as store-bought items, which I largely manage without. I made mine so that I could lower the signal generator output when needed. You can use online tools to produce attenuators using standard value resistors, which will get you pretty close for hobby work. More of that on a later slide. Here you can see that I actually tested mine on a VNA, and they got pretty close. These are the 3 dB-ish attenuators that I use when testing the filter using the simple diode probe. Using the online calculator, I find the ideal resistors that I need. Then I replace them with what I actually have. I can live with a 3.16 dB attenuator with an impedance of 49.2 ohms. It's fairly close. Of course, you can make a variable attenuator, and there are many classic designs using switched resistors. If you were to look at the PE4302 datasheet, you'd be amazed by the performance they claim. They say the PE4302 is a high linearity 6-bit RF digital step attenuator covering 31.5 dB attenuation range in 0.5 dB steps. So in Tony G3PTD's design, a 0 volt or a 3.3 volt on the V1 to V6 connections stipulated the attenuant selected, but he used an Arduino so that he could use a rotary switch. But you could use a bank of dual inline switches and not use an Arduino at all. Dwayne KV4QB went a stage further and used two PE4302 modules, and together he can achieve attenuation of up to 63 dBs. In Alan's recent very interesting YouTube tutorial, he found he needed to reduce the nano VNA output from 600 mV to around 130 mV for the amplifier that he was testing. Using a calculator, he worked out that he needed a 13 dB attenuator. Of course, you could use a variable attenuator like the one I showed in the previous slide. For professional work, you're probably going to buy those expensive pre-made attenuators, but for hobby work, the homemade ones work pretty well. Well, I hope that talk was useful to some of you, and you can see what's possible in a 5x7 garden shed. As I've mentioned, I'll be moving house soon, and it's a shame that it's not possible to take it with me. Or is it? You can do amazing things with an Arduino,